In today's lesson, we're going to talk about section 2-8, solving for a specific variable. So this whole chapter we have been working on solving for a specific variable, that's given, like such as x, when it was the only variable. But now we're going to look at a situation when we have multiple variables. And this is a tricky section for a lot of people because they get confused when they see multiple variables, but we got to keep something in mind. Variables are just numbers, and we can manipulate them the same. We can add them to both sides. We can subtract them. We can divide by them. We can multiply them. So we're going to look at some examples of how that works. So solve each equation for the variable indicated. So just like before, we've always wanted to isolate the variable, the only variable we have. Now we're just given a specific variable out of multiple variables. In this case, there are two. So we want to isolate n. So before we always said isolate the variable. Now we're going to isolate the variable we want. So we're going to isolate n. So to isolate, we need to move the p variable away from the n. So we got to subtract p from both sides. So we get 15 minus 6p is equal to 3n. And then, just like before, solve for n, divide both sides by 3. And I'm going to divide everything by 3. So I get 5 minus 2p is equal to n. And n is isolated, so there we go. I have now solved for the specific variable. Next one is a little bit different. We have k minus 2 divided by 5 is equal to 11j. So in this case, remembering back, we have implied parentheses. So we need to isolate that k. We got to get rid of that multiplication by 5, or that division by 5. So we got to multiply by 5 on both sides. So we have k minus 2 is equal to 55j. Then again, how do we get rid of that minus 2? We need to add 2 to both sides. And now j and 55j and 2 aren't like terms, so I can't combine them, so I just leave it. K is equal to 55j plus 2. And there we go. That's all there is. But now we're going to start looking at it a little bit harder. Let's keep that in mind. So now, solve each equation for the indicated variable. Now, I have d plus 5c is equal to 3d minus 1. And we're going to solve for d. Now, look at this. We have d's and c's on both sides. So I need to move my one of my d's. I'm going to decide to move the smaller of the two. I'm going to subtract d here from both sides. So I have 5c is equal to 2d minus 1. Now I got to get rid of that minus 1. I'm going to add 1 to both sides. Now on the left side, I can't combine any like terms, so I just get 5c plus 1 is equal to 2d. And then to solve for d, I'm going to divide both sides by 2. So now there's nothing I can do. I can simplify the fractions, but I'm not going to. I'm going to leave it. So I get 5c plus 1 divided by 2 is equal to d. Okay, so that's a little bit harder, but now we got a different one. This one is the trickiest of all. We have 6q minus 18 is equal to qr plus s. We're going to solve for q. So now we got a qr, meaning there's two variables in one term. Now, the biggest issue a lot of people have is, can I combine them? Well, no, they're not the same. Q and QR are not different, but I still need to isolate the Q. So I got to get all the Q's on one side. So I'm going to subtract QR from both sides. So I have 6Q minus QR minus 18 equals S. Oop. I'm going to get rid of my shade here. Okay, now I'm going to get rid of that 18. So once again, I'm going to add 18 to both sides. So I have 6q minus qr is equal to s plus 18. Now this is where the tricky part comes in. Now for this next part, we need to think back to the distributive property. Before, I'm just going to do a little example. If I had 6 times s minus 1, for example, I would get I would take that and distribute. Now I get 6 times s minus 6 times 1. Well, if I can work from the top to the bottom, I can work backwards. So I'm going to actually take away that 6, and I can go to 6 times the quantity. So the same thing applies here. I'm going to take out a q from both of them. So all I'm left with actually is 6 minus r is equal to s plus 18. So I actually factored. So now what I'm going to do is that 6 minus r is just a number. It's whatever r is, it makes a number. So I'm going to actually divide by 6 minus r on both sides. 6 minus r. Now, obviously we have all these variables, these weird terms, but there's nothing we can do. So we're left with q is equal to s plus 18 divided by 6 minus r. There's nothing we can do, and we're done. I know, so that's a little bit where people get caught up. That's a little bit trickier. So practice those a couple times. So now the formula s equals 1/2 at squared represents the distance s that a free-falling object will fall near a planet or the moon in a given time t. In the formula, a represents the acceleration due to gravity. Solve the formula for a. So I have s is equal to 1/2 at squared. So luckily, it's all multiplication, and I don't have to isolate the t, meaning I don't have to get rid of the square. And so that's good news. But now I want to get rid of that 1/2 first. So to get rid of times 1/2, I'm going to multiply by its reciprocal of 2 over 1, or just 2. So I'll multiply by 2 on both sides. So I get 2s is equal to at squared. Now, I just have to get rid of that t squared, so I'm going to divide by t squared. So now I've learned out of room here. So I'm left with 2s divided by t squared is equal to a. So now I have my formula. Now I want to use that formula for the next part. A free-falling object near the moon drops 20.5 meters in 5 seconds. Find the value of a for the moon. So I'm going to find the acceleration rate when we're on the moon. So I'm just going to plug in. Okay, so meters, obviously that's distance, or in this case it's s, and seconds is t, because it's time. So all I gotta do is substitute it and solve. So I have 2 times s, which is 20.5, divided by t, which is 5 quantity squared, and that's equal to a, the acceleration. So now I'm just going to do some essentially simple math. I might have to grab my calculator for this. Okay, so here we go. Well, 2 times 20.5, that's 41. Oh, lost my marker. So I have 41 all over 5 squared is 25 is equal to a. And 41 over 5, or excuse me, 25 is just 1.64. So we get 1.64 is equal to a. So there we go. We now know that, and the real label is meters per second squared, so I'm just going to write that for you. 1.64 meters per second squared, because we had meters on top and we had time squared. So the acceleration rate on the moon is 1.64 meters per second squared. So I'm not overly worried about the label, but that's just an important part of a word problem. So